So those are to my collaborators, and Vlad is sitting right over there. So if you have really important and complicated questions that he will be happy to answer. And Natalia did so. We have field theorist, numerical supercomputer person, and me representing the way, like Jalal says, proof by intimidation. So I'm kind of, my specialty is intimidating people into believing into the right answer. So, but what's the question? The question, more or less, of what I'm thinking all those years is to how to pass from this to this. So in a sense, if you look here, the typical angle of inclination of water is like 1% here. It's weak turbulence, so this nonlinearity parameter really very, very small. When we look here, we see angles of water unity. And so one way to say, okay, look, here we'll apply weak turbulence theory, of which too much was talked, and I a little bit more say on simpler models. Here we just say, okay, look, well, if this is a cusp, let's Fourier transform this cusp and make one over cusp squared it, and live happily ever after. Or if we're interested in omega spectra, that will be omega to the 5. This is generally wrong statement, which I'm not going to address today. I'm considering a much simpler system, but namely nonlinear Schrödinger mostly, and spin wave turbulence. But this is essentially the goal, where we hope also to apply essentially this approach. But the general feeling is that somehow something must be qualitatively different over there and over here. And on the other hand, there is this more or less more mathematical aspect of which probably Zakharov and Newell in their paper say, is there any equation for which these two could be both solutions? Let's say two asymptotics of the same equation. And then what I'll show you today is that not yet for this system, but for nonlinear Schrödinger already we have this, and for some other cases, and they teach us very interesting lessons what kind of universality appears in different limits. For physicists, the main question is usually universality, namely, you have excitation scale, you have dissipation scale, you have type of interaction here. How much depends here in this cascade interval of this scale, of that scale, of the type of interaction? And what we'll find out is that very different independency, which we call universality, appears. But on the other hand, I feel it also bears for mathematicians, particularly when you try to establish validity limit, it's really important to know how sensitive is what you observe on this or that part of the spectrum. So let me now be specific. So I consider a very particular class of system, which is still a lot of physical cases, namely, there will be set of waves with omega, or if you want, you may think about particles with energies omega p. This will be your kind of kinetic energy, or it's wave dispersion. And we have a scattering four-wave interaction. And we are mostly interested, of course, in occupation numbers. So these are the basic things which people measure experimentally, which we are interested in. Unfortunately, as everybody knows, it does not satisfy any closed equation generally. So if you compute its time derivative, it's expressed in terms of the force cumulant in this case. And then, because it conserves number of waves and energy, but I will focus today on the number of waves. So just the fact that I can write this equation as a continuity equation for the flux of particles, I always must have a solution for which this Q is constant. That would be automatically stationary solution. That's my cascade. And it immediately gives me this force cumulant. I know it. So, I mean, at this point, I know exactly what is the form of this force cumulant. It's an analog of 4/5 law of Kolmogorov for incompressible turbulence. For nonlinear Schrödinger later, I'm not sure. There are also beautiful ways to write it in R space, where it really two-point force order moment. We know it. Now the problem is to get n. Okay? So from here, more or less, everything starts that we know force cumulant, and we want to find second moment. And there are different limits in which you can express one through another. And in particularly, one of the limit is if this nonlinearity is very, very small. But essentially, whatever I'll be doing today, it's always will be the same trick. We are one trick pony. So we assume that the statistics of amplitude is close to Gaussian. And it's very often that people sell you different computational scheme by different names, claiming that they described really a very non-Gaussian regime analytically. Never ever seen this working. Okay? So even though what I will try to show you how we will go from this lambda be very, very small to this lambda will be very, very large, there will be extra parameter of smallness, which would again guarantee that in some right variables we are close to a Gaussian distribution. I really want to be honest here. Right? There are no free lunches in this science. But one of the simplest case, of course, if you assume that it's exactly Gaussian and a set of independent weights, namely this is a product state, then of course the cumulant is zero. So you need to compute the first correction to it, and you obtain a standard kinetic equation, Peierls kinetic equation, if you wish. And now, of course, because this is your expression of your force cumulant, this is your force cumulant now expressed in terms of nk, then by requiring that it's constant and by power counting, you immediately obtain this solution. Let's see what it has and what it does not have. First of all, it depends on your pumping level, how strongly you pump. It depends on how strongly you interact, but essentially kind of only scaling of this interaction, which is this factor, that's what is beta here, then is m here, I apologize, it's the same number. So it depends on the scaling of your interaction, on scaling of your omega, and how strongly you pump. It does not depend on your wave number at which you source and at wave number at which you dissipate. Now, how it's possible that it does not depend? You prove it like this. Again, it's a physicist way of proving. You plug this into here, and you show that it turns it into zero if you consider it on infinite intervals, and you show that all integral converge. It's very important. As long as integral converge, they do not depend on their ends, either infrared or ultraviolet, as physicists say. So then what you do, of course, is, first of all, if this equation valid, which, like we discussed many times, with 40 years with Zakharov, we believe, of course, it's valid. Why would we worry? Now, after 5 years of this beautiful collaboration, I'm starting to see subtleties in this question. And particularly, I want to notice that this is a power law. Right? And when you plug it in all these beautiful high diagrams, all hell breaks loose. So at this point, I am on a physicist level. When I'm claiming that this equation applicable and this is its solution, I am on a very, very slippery ground. But I'll proceed from here anyway, and I'll do the next step. And the next step will be I compute correction to this equation. Namely, at least on a physicist level, if you want to show its validity, I at least need to compute next correction. You know, this is a beautiful thing about trying to do many other things, and we'll talk a little bit. But for far, let's just compute first correction, which would be lambda cube. So there will be 3 lambdas to it. Again, symbolically, we present it as a diagram, and physically, it's pretty kind of transparent. You say that essentially, I renormalize. It looks like the same kinetic equation. You see this bracket, which immediately tells you that the moment you plug here equilibrium, thermal equilibrium, it turns into 0. So no problem for equilibrium or near equilibrium state will be here. Only when we plug here turbulent solutions, then we'll see interesting things. Right? And it has 3 lambdas. Good. So now let's take it, because I assume that I am close to weak turbulence. So I may assume that my solution is close to Kolmogorov-Zakharov solution. So now I plug Kolmogorov-Zakharov solution in this equation. And first thing that and then I see that it determines by 2 dimensionless, what we call loop integrals. This is naively saying is my nonlinearity. It's lambda times n integrated over k and divided by omega. This is by power counting just my nonlinearity parameter. At the beginning, I assume it's small. But it's an integral now. It's not lambda at a given k times n at a given k divided by omega at a given k. It's an integral. I need to integrate over all 5, 6, which are intermediate waves. There are waves 1, 2, 3, 4, but they interact through 5, 6. and I need to integrate over all possible wave numbers of 5, 6. And the first simple questions that I ask, if it's positive or negative, I enhance interaction or I suppress interaction. Then I immediately see, as anybody who did perturbation theory knows, that there are denominators made out of omegas. And they contain this 5, 6. And 5, 6 run from 0 to infinity, technically, or from source to dissipation. You immediately recognize that it changes sign. It's a very simple physics, at least the way that I intuitively understand. So in a sense, you have waves 1, 2, and they produce some intermediate state with the frequencies 5 plus 6. And if this omega, let's say here is 5 and 6, if they are larger than this one, that you would give minus, which means that just imagine that you have a oscillator which you try to force by some external force. When the frequency is less than the resonant frequency of my oscillator, you are in phase. When it's higher, you are in antiphase, you are pi. So you change sign. So you see this change sign, so you understand that it's not that simple even to establish sign of correction. Namely, you need to integrate over all this stuff, and it very much depends on this terrible lambda. And then, of course, for waves on the water, we're still work in progress. So let's it's just, I mean, this is a correction, so it's technically need to be linear in lambda, but you see it's lambda divided by lambda. Because I took it out, if I'll show you the previous slide. So you see, that's my correction to kinetic equation. But I won't present it in the usual form in which this lambda stays squared. So I took it out squared, and it gets here in the denominator. So my correction is now dimensionless. Okay? So now I'll start one by one from the simplest case. The first simplest case is constant lambda and omega k squared. This is a nonlinear Schrödinger. And of course, we are very much interested in this lambda being positive or negative. We suspect that they're very, very different strong turbulence. Even though weak turbulence does not depend on the sign of lambda, it has lambda squared, as usual. Good. So now what I'll do, I'll look at this Zakharov solution. I'll compute next correction, and I'll see how holes that we built for these 40 years crumble into pieces, and then we'll try take these pieces and build something out of it. So here are pretty technical but more or less straightforward computation. So you plug, so this is your two loop integrals, now called, to confuse the reader, L plus L minus. Here you're supposed to plug the Zakharov spectrum. You plug it, you obtain the result. Here is the result, and it again depends on different angles, etc. Overall, it would give you the conclusion, which is written over here, and I would reiterate it over there. So the sign of a correction behaves as a minus lambda. If I translate it into simple physical meaning, it tells you that when lambda is positive, namely I have repulsion of particle or defocusing of waves, then this interaction is suppressed by 6-particle interaction. So I'm asking, what is my 4-particle interaction renormalized by accounting for other two waves? The answer is, if it's repulsion, it's suppressed. If it's attraction or focusing for waves, it's enhanced. That's simple conclusion, which already was in our first paper. So now, of course, it immediately rings a bell about Lighthill criterion of modulation and stability, because Lighthill criterion says that if you take your lambda and multiply by omega 2 prime, which in our case is just number 2, it's a second derivative, but generally you may consider different waves. Now, the sign of it determines whether you are modulationally unstable and go into collapses, self-focusing, and other things. And we see that what we obtain, in a sense, a turbulent analog of this monochromatic wave instability statement. So what we now say is that if in the defocusing case I suppress my interaction, so here is my weak turbulence. It does not know which sign lambda is. I go by this cascade. At some point I start feeling suppression of interaction in the defocusing case. To carry the same flux, I need to have more turbulence then. So what is our prediction for just first perturbative correction? That when you go in the defocusing case, your spectrum is supposed to go up, and in the focusing is supposed to go down. This is simple things that you conclude on this, what we call one loop correction. We only accounted for one loop integral. So now we want to know where we eventually go. It's clear already that strong turbulence will be vastly different in these two cases, and we now want to see how different it will be. So now, oh my God, what is it? Okay, good. So we used to joke with Zahara many years ago that, you know, there was the first transparencies appeared and people started to write equation in different colors. And I remember we were joking, you either solve equation or you color it like kids. So this is, I tried to color this equation and it did not come out. Hopefully, it's probably PDF file. Yeah, I did not expect it. Sorry, so probably it will come somewhere else. So what now we'll do to go into this large lambda regime. So now I want to consider large lambda, okay? Namely, I want to pass from a limit lambda going to 0 into limit lambda going to infinity, but I need some extra parameter, because again, I'm not a miracle maker. I only can compute anything which is close to Gaussian distribution, but it will be very different Gaussian distribution that one was before in terms of occupation numbers. But the whole statistic will be still close to Gaussian distribution. So you do it by assuming that your psi is a vector. Like in near-Navon experiments, you can have different sorts of particles and, let's say, different spin configuration of your cold atoms, and they would be, so you assume that this n is very large, and then you can actually compute to all orders. And yeah, let me see if I have somewhere this equation. Yeah. So the equation which was colored there, and fortunately is uncolored there, is this equation. So what appears after you assume that your n is large, you consider leading order in n, and sum all terms in all orders of lambda. But at every order, you choose the largest term in n. Fortunately, for this particular case of nonlinear Schrödinger equation, at every order, you have only one term, and this term of all orders create geometric series. Actually, two geometric series, but it's more or less straightforward. And then this series is summed into this term. This is the same loop integral, one of them, L minus. So what we find out in this limit of very large n and arbitrary lambda is a kinetic equation having the same form, but renormalized vertex, renormalized interaction factor. Now this L, as you remember, is an integral which itself depends on n. So this is this new equation which rules them all weak and strong. When this L would be very small, we are back to classical Parallels equation. But now we're interested what happens when L would go and increase and getting larger and larger. And now we encounter this thing that the sign of this L is really very important. Because if this L, your loop integral, is negative, then there is no problem. You increase and increase and increase. You pass through unity. It's getting very large. You go into strong turbulence. And eventually you see suppression. As long as this will be very, very large, your interaction effectively is suppressed. So you expect it to be in the defocusing case. But then you also know that this L could be positive. Namely, you have enhancement. Then you start approaching unity over here, and this enhancement is getting pole-like. You're starting to approach infinity of interaction. And that's what we now try to sort going into this thing. So now let me get back and one by one consider this. So just maybe one word that I say here is that for physicists, what really it brings to mind the analogy of renormalization of interaction in quantum field theory or in critical phenomena. In particular, the first maybe clear example was just you take two charged particles but you are in a quantum world, which means that the vacuum in between them is filled by fluctuating, appearing and disappearing, pairs. And you ask what it gives to this interaction. And the answer is it screens, which tells you that the particle which appear there, they do make your medium, namely quantum vacuum, polarized, which tells you also the following thing: the farther away you move these two electrons, the weaker is the interaction. And this is a subject of quantum electrodynamics. But what was surprisingly found later, and also got its own Nobel Prize, is that there could be two different cases. That this renormalization could go such that this beta, this traditional notation beta, would be positive or negative. Namely, that for it's sometimes called anti-screening, sometimes it's called confinement or asymptotic freedom, but when you look at inside protons and you scatter very high energy particles, you find out that quarks which live inside almost free. I mean, they scatter your very energetic particles as if there are no other quarks around. But on the other hand, you don't see quarks outside of a proton. And so this idea which came out of it and which effectively, it's still not theory which not built. It's just a sign that people found and for which Gross, Wilczek, and Pulitzer got a Nobel Prize, is that when you increase the distance between two quarks, the interaction grows, as if there is an elastic band which you stretch more and more and more. So this is a physical analogy which inspires us in our consideration of our kind of sorting out suppression from attraction. And again, we are moving in the inverse cascade to larger and larger scales. So in a sense, I'm saying, I have a small scale waves, they interact weakly. I'm now doing inverse cascade, I have longer and longer waves, and asking how the interaction is actually renormalized. And the answer is that it depends on the sign. So let me first start from the defocusing case. It's kind of simpler. Then in this case, my lambda is positive. It's a repulsion. My first order correction was negative, namely it's suppressed. So now I assume that in this denominator, because this is now negative, I can safely pass unity and go to the limit of very large L. But now I find very interesting and to some extent unexpected, at least for me, new universality appearing. Namely, this lambda, small lambda, drops. This is my original interaction, which I computed just by computing refraction index of my material and seeing how it depends on light amplitude. Yeah, this is something which I measure. This is measurable quantity. It totally drops out because my L also proportional to lambda. So the moment I forget this unity, this L is very large, I find out that my effective interaction, first of all, indeed goes to 0 when k goes to 0. So it's asymptotic freedom. They're weakly interacting particles. It's also very, very non-local. Namely, this integral diverges and proportional to the total number of waves, and this integral is in the denominator. So this is kind of ultimately, this is the weakest interaction you can imagine. The energy of interaction is an energy or frequency of a given k divided by the total number of waves. So all waves participate in suppressing repulsion of two waves. Yeah.
Then the denominator in your
by summing geometric series in all orders of lambda. That's how you do. So you technically write your perturbation series for your kinetic equation. At every order, you choose only the term which is largest in this n, which is my vector, which my size of the vector. Then you find out that in every order, the strongest term is called ring diagrams. Is it people? What I'm doing in quantum field theory is a standard thing, and Krigman derived this formula in 1955, 4. I mean, Schwinger derived this formula. Everybody and his grandmother in quantum field theory did this trick. Assume that your field is vector of a very high length. Then any scalar product, you can apply central limit theorem, just because there are so many components in a scalar product, it's close to Gaussian. And then using this, you can compute all your high orders, the main terms. And it happened to be that they just could be summed into a geometric series. Okay? So you see now that this is something which, if you expand up to first order, you get 1 plus L. That was our what is called one loop correction. These all ring diagrams summed all together, so it's arbitrary order in lambda and the leading order in n. That's the meaning of this equation. So now we want to explore it and see how much really it can describe us. So for defocusing case, it gives us universal behavior in terms of effective interaction. It behaves like frequency. It's strongly suppressed. It's like you create a locally very homogeneous, like precondensate states in which all the other waves effectively switch off in interaction between these two waves. And you see that actually my original lambda was constant, right? It was independent on wave numbers. This is dependent. The smaller k is, the weaker is the interaction, or the higher is the energy. If you on cold atoms, it means that the fast particles can really, fill inhomogeneities in your precondensate, and they do interact stronger than very slow particles that go around. And this is defocusing case. And now using this new vertex, you can ask again, because you have a kinetic equation, what is the new solution? And the new solution, again, is like it used to be q divided by lambda squared, but lambda now is different. So this is your new solution, which totally independent on your bare interaction lambda, but it depends on your infrared of your largest scale of the problem, because your integral diverges at low k. You remember, in the defocusing case, my spectrum go very steeply up. So this k naught, or in other words, the total number of waves, is a parameter. So this is the first universality class. You go into strong turbulence through suppression of interaction. You forget your original interaction, but you do know the destination of your cascade. It's a dramatic statement. This k naught is a dramatic statement. Like, this is where my cascade ends. And I'm now looking here at k, which is much, much larger than where it ends. I already know where it ends. It's, speaking to Nazarian, it actually tells you that this is something which will be two stages of establishment. The temporal kinetics is very interesting here, right? But the steady state knows the destination of a cascade. That's the meaning of this stuff. Now, let's go to focusing case. In this focusing case, again, this L is positive, so you cannot technically pass, even though when you start numerically solving it, the computer can take you through unity and you can go into this large L limit. So what is the solution in this particular case? And it's an analytic solution, namely, we can show that if you take n in this form, particularly for 2D, I guess for 2D, it's even, for 2D, it's just an exact computation. So this is my, and I assume that my L is in the main order is unity, and then correction proportional to this, and then I can prove that the resulting state will be a constant cascade state with an effective lambda, which is 1 over k squared. That's how it's enhanced for focusing case. We're now describing occupation number in a state with many collapses. It's strong turbulence. Okay? First of all, the amplitude of this state totally independent on the flux. That's what we would expect, because if your interaction increases, eventually it needs to bring you to something which restricts this, and those are collapses. And this is, again, this 2 dimensions, at least in 2 dimensions, this is a solution. For 3 dimensions, power counting suggests, but we don't know it. We did not solve this equation for 3D. For 2D, we did solve this equation. That's an effective interaction. It depends on the bare interaction. It depends on Q, but this solution does not depend on Q. Okay, so now let me kind of sum this up. So if you have a general formula for, but here, what stands here is either this interaction or that interaction in 2 different cases. And in one case, it gives you lambda independent answer, and in another case, it gives you Q independent answer. So that's kind of two new universality classes, and this more or less schematically are shown here. So you go from weak, you go up, you go down. Now, if you look at these states, which are in the focusing case, you increase Q. Let's say here is your pumping. So here you go into strong turbulence. You increase pumping here, okay, so you go into your turbulence early at larger K, but you go into the same state. It's independent on your level at pumping. On the other hand, in the defocusing case, again, it's a prediction of our considering limit of very large n in this very special equation who can rule weak and strong turbulence. Now, if you change lambda, again, you go, when your lambda stronger, you need less waves, so you go down, but eventually you come into state which is independent on lambda. But of course, it depends on flux. So that's our prediction, and that's more or less these two universality classes, and those are direct numerical simulation of one component, usual complex scalar nonlinear Schrödinger equation or Gross-Pitayevsky equation, done both by focusing and defocusing case. And that's weak turbulence, which does not occupy much. It's pity to waste computing skills, but and this is a pumping scale, and then you see the defocusing case go sharply up, and that's our prediction without any fitting factors. And this is a focusing case which goes into a constant state. So at least on this basic level, we see that the prediction that weak turbulence at large K parts way and goes into two different types of universality, it's more or less supported by numerics. There are more data, and again, that was something which also in the Georgia and Nazarenko 3D computations, they've seen in the defocusing case, the state of a spectrum is very, very sensitive to how you organize your absorption or sink for your inverse cascade at low K. As long as you keep here, it's really absorbed, you see this part, which is in our case 8/3. In 3D, we predict 11/3 for this case. But the moment that you kind of allow here to grow, which would then will be a condensate eventually at low K. This is a defocusing case. You start seeing different deviation in this spectrum, and you can also look at the statistics, and you can locally look what is the probabilities of big semi-homogeneous, what Natalia calls precondensate. So it's not very easy to get it, but again, at least on this level, what I really want to stress, this is n equal to 1 direct numerical simulation. It qualitatively and even quantitatively corresponds to large n kinetic equation, which obtain using absolutely extra parameter, which here is equal to unity. This is not something that we can prove. It's just, we can accept it as a gift and try to use. Okay, so this probably I'll skip it. Again, that's the focusing case, and you see how through 5 orders of magnitude of increasing flux, the amplitude of a spectrum change, it actually depends a little bit of the dissipation at large beta, but it changed like a little. This is universality of a focusing case. No matter how strong you pump, everything goes into collapses. Your occupation number, statistics is very, very non-trivial here. So if you really go to higher moments, they won't be described that easily. But occupation numbers through 5 orders of magnitude, this is direct numerical simulation, nonlinear Schrödinger focusing scalar case. So this is really something which look reassuring. So let me kind of make intermediate conclusion, and maybe this is a time to ask questions, because I'm finishing with nonlinear Schrödinger, and I'm going into even more surprisingly cases. So again, nonlinear Schrödinger is a statement that you do inverse cascade, you go from weak nonlinearity to strong, focusing interaction increases, which suppresses the spectrum, which eventually comes to a constant independent on the pumping. Defocusing case, you suppress interaction, turbulence level goes up, it eventually comes to the state which is independent on your interaction, but very much dependent on the total number of waves. Questions?
So suppression and enhancement that you get analytically is in the large N regime? And then you show simulations for N equal to 1, which seems to have the same trend?
No, you can see suppression or enhancement doing a first-order correction. But again, because this first-order correction depends on configuration, you need to integrate over configuration, because there is no simple answer that all interactions are enhanced or all interactions are suppressed. As we have seen in the first-order correction, some are enhanced, some are suppressed. But the integral effect you can compute for any n. It's just you can do one loop correction to kinetic equation. You need large n to go to very large lambda. That's what you needed.
Questions? In your derivation, you assume to be close to Gaussianity.
Yes. When
Have
you
you
do
checked with DNS that you are?
Oh, DNS is never ever close to Gaussianity in the limit of strong turbulence. That's the beauty of it. That's something. I mean,
there is a contradiction there.
This is a very good question. So, in a sense, what we do, we use large n approximation. By these large n parameters, I am in some sense close to Gaussianity. In what sense? For example, if I want to compute force cumulant, the only thing we compute in this large n limit is a correction to the force cumulant, which is the right side of kinetic equation. This is done correctly, which this shows you. But on the other hand, if I would like to compute, for example, 6/8 order cumulant, namely, or look for the tails of my probability distribution, that would not be working in the sense that my large n approximation does not describe this. The fact that it describes qualitatively decently the statistics of the form of occupation numbers for n equal to 1 case, it's something which I cannot derive. That's just what happens. But n equal to 1 normal nonlinear Schrödinger in the limit of strong turbulence never ever close to Gaussian statistics. Look, this is a set of collapses, for God's sake. This is very non-Gaussian. But occupation numbers are correct. That's the beauty of it.
Any other question?
Okay, so now, as long as we learn this trick, which incidentally a pretty standard trick in quantum field theory, the people use this large n pretty often, and I mean, people at Heidelberg try to apply it to turbulence, but for direct cascade, for some other cases, which I don't think that it's really that was illuminating. But so now we can apply it to other system, and I show only one example, which is still kind of really surprising and brings us to the next level. And it's essentially, it's almost the same Hamiltonian. That's the only difference that for here is, you can, I mean, this is just your spin, and you can assume that you are in a state of almost good ferromagnet, so all spins are almost look in the same direction, just a little deviation would propagate as spin wave. It's just a wave of precession of angular momentum. So this deviation you can characterize by a psi, and then again, assuming that this psi is small comparatively to unity, you can expand your Hamiltonian. There are, of course, sextic terms, there's the whole enchilada, but at this level, so it's very much like nonlinear Schrödinger. The only difference is this gradient. I very much want mathematicians to pay attention to this, because it's first of all, it's no less important than nonlinear Schrödinger. It's a next in complexity, in the sense that your lambda now is still pretty simple. Kind of, it's not that terrible, right? And there was not mathematical work on it, and I think it deserves attention. But now it's something completely different when you start to doing your you can do usual weak turbulence, etc. You can introduce your parameter of nonlinearity, which is again lambda n total number of waves divided by omega. But then again, you can do inverse cascade. Again, you find out that your inverse cascade is getting strong when you approach lower k. and then you can do this one loop corrections, and this your one loop correction that you obtain. And now when you look at these lambdas, you find out that, you remember, this is P5, P6 plus P3, P4. And this is P5, P6 plus 1, 2. So now your convergence condition for this integral very much depends which part of this sum you take. And so you find out that there are now different what we call loop integrals, namely that there are in some, this R could be 0, namely in this product you just took 1, 2, 3, 4 only, or this could be in the first power, it could be in the second power. So we have this L0, L1, and L2, 3 different loop integrals, and you find out that L1 with this, which like original loop integral for Schrödinger, converges. L0 diverges in the infrared, normally at large scale, and L2 diverges at very large wave number, at UV. So you find out that in this simple case, if you compute first correction to kinetic equation, plug the Kolmogorov-Zakharov solution, the correction depends both of the smallest scale and the largest scale of your cascade. This is the first surprise of this system. And then again, we don't know how general it is. So for Schrödinger was all was converging and divergences appear only in strong turbulence. Here we have these divergences appear over there. And now, because your lambda is more complicated, it's not a single geometric series, and it's, I mean, I would never do this. This Vlad Rosenhaus did this. So this is an integral equation, which, again, in the limit of very large n, when you consider your field a vector with very many components, you get this integral equation. For Schrödinger, when this lambda was a constant, this lambda was a constant, the solution was 1 divided by 1 minus L. Now, the solution is much more complicated. It's essentially a result of 3 different intertwined geometric series. And this, I mean, ask Rosenhaus how he found it, because I would not find it. But this is the answer. This is a solution. Surprisingly, it's a closed form expression of your new interaction in terms of your bare interaction. This is just P1, P2 plus P3, P4, and 3 different loop integrals. And so now, in this case, again, you can do all the same. So you have your kinetic equation, which has a usual form, but it has this guy over here, and you need to go from weak turbulence to strong turbulence to lower and over K. And again, I probably will spare you all this, that we find out that in this case, independent on what was the sign of your, remember that the interaction for spin waves, where is my, yeah, it has this lambda. So again, you can consider cases of positive and negative lambda. No difference in this case. Because essentially, when you come and look at this unbelievable expression, that what comes here is L0, L2. Essentially, this term is determined, but L2 proportional to lambda squared, and L0 is independent on lambda. So both cases, lambda positive and negative, give the same result. Then again, because it also depends on direction of wave vectors, so, and the result is enhancement. What do you mean in the limit of 0 epsilon? Oh no, what I'm saying is that my ultimate state is that this denominator approaches 0.
But you regularize the exact time resonances, right? In your expression, there is an epsilon there.
Yeah, of course. When your integrals over this omega, these are Cauchy integrals. You need to understand them as Cauchy integrals, which you can write in temporal domain. It will be just long time integration. It's pretty standard procedure, but you need to be careful. It's principal value integrals. Okay, but what is the last thing that I want to say, and this is probably the most surprising, for me at least, I did not expect it, is that the result of this solution for spin waves depends on the maximal wave number at which it is realized, or if I retranslate it in a more simple terms, it tells me the following things. That you remember for Schrödinger with focusing case, it's similar to Schrödinger with focusing, but with important difference. I increase my forcing up to here, but eventually it came to the same spectrum at low k. The strong turbulence was the same. What happens for spin waves, and this was a really total surprise, is that you increase here your pumping, that your spin wave turbulence, it comes earlier into the strong turbulence regime, but the strength of interaction here depends, because it's a divergent integral, it tells you that it's stronger interaction because it's started at larger k, then its level is lower. I just really want it to sink in. I increase pumping at weak turbulence domain, and level of turbulence in strong turbulence domain goes down. That's a prediction. Nobody have seen it, nobody modeled it, etc. But that's a prediction until I make my turbulence strong already at pumping scale. Then it stops changing. But if my pumping excites weak turbulence, increasing pumping increases level of turbulence in weak turbulence domain and suppresses it in strong turbulence domain. It's as bizarre as one can get in turbulence theory. Again, nobody have seen it. And so now let me finish with it. That first of all, it's no miracles. It only works, at least it has a domain of applicability when n is large, namely that my field is a vector field. Even in this case, what you essentially obtain is a renormalized kinetic equation with a renormalized vertex which satisfies an integral equation. What we did, one trivial and another by miracle, is that we solve this for two simple cases, constant lambda and lambda which is P1, P2 scalar product. But it could be solved numerically for, let's say, waves on the water, or for other waves. So this is something which is now a new equation, namely you have two integral equations. So in a sense, what you do, let's say numerically, you iterate this, you obtain n, you plug it here, because this n's here, right? So the solution of this equation depends on n. The n depends on solution of this equation. But it's something which is a closed system of equation on a single quantity occupation numbers. And in principle, it works in the limit of strong turbulence and weak turbulence. When you're in the limit of weak turbulence, you neglect this term, you have this, you have just bare interaction. When you're in the regime of strong turbulence, it could be that this is of order this, or this is of order this, which is, in our case, was different between focusing and defocusing. So in this sense, I think that this is a new equation in its most kind of general setting. I think it's very interesting mathematical object, and it gives physical results which are, let's say, interesting and unexpected. So let me finish this point.
Thank you, Risha.
Can you hear me?
You.
I come back to my question with this. When we use, I like to use a multiple time scale technique to get the kinetic equation. And then if you do that, you have different time scale, T0, which is the wave times, and T1, T2, T3, and T4, the times that you have for this problem. And in weak turbulence, of course, in T1, T2, T3, there is nothing. But then if you perturb your system like what you do, you should get, I mean, in principle, I think you should get something at lower time scale. So how do you, I mean, why we should not get anything at T1, T2, and T3 in the closure?
No. At this point, I'm not, generally, when you do usual kinetics, you have lambda, your parameters. Let's just talk about lambda. So when this lambda is very small, you have your kinetic time, which is kind of very, very large. And you say that this is, really things happen slowly because my interaction is very weak. But now you have instead, you consider that your lambda is arbitrary, but your hierarchy appears because of n, not because of lambda, okay? And in this sense, again, you have a time which is related to n. Now, before it was proportional to 1 over lambda squared, kinetic time. Now it's proportional to n squared. So in this sense, n takes a role of lambda. But the computations are much less trivial because for lambda, you just need to take the first non-vanishing term. For n, because you want to consider all orders of lambda, you take leading order in n, but it contains to infinite number of terms in lambda. So you sum these terms. That's the thing that you do. Now, what are validity limit of this equation? I have no idea. And you never ask physicists about validity limit. But when you ask me about Zakharov's equation, namely without this guy, validity limit, I cannot answer you before I compute first correction to it. So you need to compute 1 over n correction to it, and then you'll see its validity limit, at least in this sense of, like you said, multiple times, because your times now are classified by n, not by lambda.
It works. So from kind of what I gleaned, the derivation kind of plugs in the Zakharov solutions in, and I'm trying to just explore if this correction of the theory would lead to change in a prediction in the inertial range, especially the slope, right? This kind of reminds me my work with Oliver for the MMT system, where the slope kind of seems numerically, as with simulation, seem to depend on the dissipation. And this is kind of getting, right.
No. Only in the first part of the work, we used small correction to Zakharov, and we plug Zakharov solution in. This equation has Zakharov solution only in one limit. In this case, it will be large K limit. But on the low K limit, the solution is very different from Zakharov's. Again, you remember this? It started like this. For defocusing, went very far away up, and for focusing, very far away down. So in this sense, in the opposite limit of very large interactions, it has nothing to do with Zakharov solution. It's very different. That's why it rules them all, weak and strong.
Anyone else? So I do have a question. You haven't mentioned anything about the transient, like the blow up that you expect for the.
Yeah.
How does it change?
Yeah, this is I mean, somebody would suspect that I tipped Giorgio to ask me this question because I very much wanted to talk about this, but it's still something which is very, very speculative. Because in particularly, for this, I need to go to the simple version of Schrödinger. But this may be one of the selling points. So let me be a marketing agent of myself, or of this equation, okay? So why I want mathematicians to pay attention to it? It may have a very bizarre and interesting properties, particularly for Schrödinger, is that it may have a very strange type of finite time singularity, which I've never seen. So this is focusing case only, and that's what we are working now on, but then again, it's... So when I'm claiming that my stationary solution is when L approaches unity. But when L approaches unity, this kind of blows up. So what I suspect, just naively saying, that this is ddt, it's proportional to the deviation from steady state. But this is also proportional to deviation of steady state. Technically, you can say that ddt is proportional to 1 over ddt, so it would give you square root singularity in time. That's my fantasy, which now we try to, and it's very difficult to find these things, but which means that this is a very interesting equation. You've never seen anything like this. What I'm saying, kinetics is bizarre. In particular, this denominator in the focusing case, which is close to 0, can give you something when you approach steady state by accelerating. I mean, I've never seen anything like this. It's usually you go into steady state and you go slow, because in steady state you stop. So this is how you can stop by accelerating. I don't know, but this equation may have such solution. Thank you, Giorgio. Actually, was
Exactly, but my
I
question.
was ashamed to give such fantasies.
Very quick, because I think my question was more in the type of condensation blow up. When you start from some narrowly supported initial condition, and you know that in finite time it will blow up at 0.
Good question. I don't know the answer. So in a sense, you're right. So now if I look at weak turbulence, I know that my inverse cascade is self-accelerating. We did not study this for this equation. It's a very good question. Yeah, it will be different for focusing and defocusing, of course.
Any other question? Gregory?
Usually there are ultraviolet divergences in higher order bubble diagrams. So when you resum them, do you need to regularize them and set the scheme through confrontation with experimental data, or you do something else?
The divergences depends on what kind of a spectrum occupation number you have. So what we find out that for defocusing case, the spectrum is getting so steep that there is no UV divergence, it's only infrared. But for focusing case, the spectrum is getting like this, and all the divergences are UV, and you sum them. And for spin waves, it's even more that your solutions start to depend on this UV cutoff. But only when you like focusing, namely you make your spectrum less steep, then the small scales start to matter.
Okay, I think that's all for the questions. So let's thank Grisha for this wonderful talk.